Having explored substitution reactions that operate by SN1 and SN2 mechanisms in the previous chapter, we now need to turn our attention to elimination reactions because we find that elimination reactions often accompany substitution reactions because the reagents have similar properties, and under identical conditions you can often get a mixture of both substitution and elimination. That's what's illustrated here. If you have a substrate, like we've talked about previously, where you have a good leaving group attached to carbon, we've explored the two pathways by which a nucleophile can interact with these substrates, either by direct substitution by SN2 or by ionization to form a carbocation and then addition of the nucleophile to that carbocation. And those mechanisms lead to substitution products. But the same features of the nucleophile and the substrate can also lead to a competing pathway where we form a carbon-carbon bond. And these are called elimination reactions because we effectively eliminate a hydrogen and a leaving group. The nucleophile, which is a Lewis base, can, under certain conditions, act as a Bronsted base and remove a proton from this species. And we're going to find that there are two different mechanisms by which that can happen. So those mechanisms both lead to the formation of alkenes, of carbon-carbon double bonds. So our first elimination reaction operates under what's referred to as the E1 mechanism. The E1 mechanism competes with SN1 because the first step of both of these mechanistic pathways is identical, and that is loss of a leaving group to form a carbocation. And so this is a mechanism that would only operate if the leaving group were attached to a secondary or tertiary carbon and lead to a reasonably stable cation. As we saw previously, if a nucleophile acts as a Lewis base and adds to that cation, you form a new bond between the carbon and that nucleophile and you get a substitution reaction. But nucleophiles, by virtue of non-bonded pairs of electrons, also have the ability to act as a Bronsted base and remove a proton, act as proton acceptors. And if that proton is removed at a carbon adjacent to the carbon that bears the positive charge, we get a carbon-carbon double bond and form an alkene of some sort. The main difference is the basicity of the nucleophile. So if you have a highly basic nucleophile, then you see a preference for the E1 pathway in the formation of alkene products. Whereas if you have a highly nucleophilic nucleophile that has a low basicity, you favor the SN1 pathway. When the reaction does occur to give elimination under these E1 conditions, we find the rate equation looks like this. And you'll notice that that rate equation is exactly the same rate equation that we see in an SN1, where the rate of the E1 elimination is entirely dependent on how fast the substrate undergoes formation of the carbocation. So we see the rate law is dependent on the concentration of one population of the substrate molecules, and hence the designation 1 after the E. So here's an example of how you can kind of lead to the same products but in different proportions depending upon the basicity of the reaction conditions. So here we have an excellent substrate for forming a carbocation intermediate. So this is, of course, a tertiary alkyl bromide. Tertiary alkyl bromides can undergo cleavage of the carbon-bromine bond and form relatively stable tertiary carbocations. If the reaction is carried out simply in ethanol, then the majority of the product is what we have talked about in the previous chapter, where we get addition of the oxygen of the ethanol to the carbocation, and then after deprotonation, we would lead to an ether product that would have a structure that we see here. And in fact, under kind of just conditions where we warm this substrate in ethanol, we get about 80% of our product mixture is in fact that SN1 product. But ethanol is also a weak Bronsted base. Has about the same basicity as water. It's, after all, essentially just an organic derivative of water. And it can deprotonate the substrate and lead to an alkene product. And about 20% of that reaction mixture under those conditions is the alkene. If we add base to the ethanol and create a solution that is a mixture of sodium ethoxide in ethanol, sodium ethoxide is the conjugate base of ethanol, so we have some concentration of ethoxide in that solution, then we find the proportions of these two products shift dramatically and favor elimination. And you can see under this set of conditions, we're actually getting 93% elimination and only 7% of substitution because of the strong Bronsted basicity of the ethoxide ion. Ethoxide has the same basicity as hydroxide. You want to think of this as just an organic derivative of a hydroxide ion. So let's draw the mechanism for an E1 elimination of this T-butyl bromide just in ethanol. So I'm going to use bond line formulas to illustrate this mechanism. And the first step of our mechanism is just going to be ionization, in the same way that the first step of an SN1 mechanism is ionization to form a carbocation. And so we would form this carbocation. In an SN1 reaction, a nucleophile would add to that carbocation, but in the E1 pathway that leads to elimination, then the nucleophile is acting not as a nucleophile, but rather as a Bronsted base. And it's going to remove a hydrogen on a carbon that's adjacent to the carbocation. I'm going to abbreviate my ethanol this way. And so it's going to act as a Bronsted base. So it's going to take the proton, and that leaves this pair of electrons behind to form the pi bond. And there's our alkene product. And finally, to finish up this section, I need to note that with some substrates, there's the possibility of forming different alkenes because you have hydrogens adjacent to the carbocation that, when deprotonation occurs, leads to the double bond in different places in the structure. And this is a very good example of that. Here we have 2-bromo-2-methyl butane. So if you look at this substrate, it's a tertiary bromide, so it's very readily going to ionize because it can lead to a tertiary carbocation. So here's that tertiary carbocation, and deprotonation now can occur either of these methyl groups at this end, and those either methyl group leads to the same product. If the double bond is in this other position down here, it's actually the same compound, and so you would get this alkene. But deprotonation at this position leads to the double bond here in the middle of the molecule. So back in the end of the 19th century, a Russian chemist by the name of Zaitsev, and you'll see this name spelled phonetically various ways, but it's pronounced Zaitsev. He was actually a colleague of Markovnikov, and you remember Markovnikov from earlier. Zaitsev looked at these types of elimination reactions and made the observation that when you have the possibility of forming double bonds in different places in a structure, so here we could form the double bond here in the middle of the molecule, we could form the double bond here, His observation was that the reaction favored the formation of the more stable alkene, the more substituted alkene. So if you look at the two products and think back to what we learned about alkenes, these are isomers. This one should be the more thermodynamically stable isomer because it's a tri-substituted double bond. The other product is only a di-substituted double bond in that way. Now, the other thing I want to draw your attention to are these percentages here. You'll notice this is 32% and this is 8%. So we're getting significantly more of the more substituted double bond, and we're getting significantly less of this less substituted double bond. Now you might ask the question, that doesn't add up to 100, so what's the rest of the product mixture? And the rest of the product mixture is the competing SN1 reaction, which actually is the major product from the reaction. And the major product from the reaction we can draw is the SN1 substitution product. And that makes up the bulk of the. So the reaction actually favors substitution, but this is the elimination reaction that's competing with it.